Hey, discrete math students, and welcome to this extra example video. So we're going to be considering a quantified statement in this video, and it in fact is a multiply quantified statement. It's got both types of quantifiers. Those kind can seem a little intimidating. Now, the process to follow here with these is as follows. So suppose that you want to negate a multiply quantified statement, which is what we're going to be doing. What you do is, don't get overwhelmed by trying to look at the whole thing at once. You just kind of start at the beginning and you take it one step at a time as you go through the statement and negate each piece as you come to it. Now, it's easy for me to say that that's easy because I've done it a lot, but experience has shown that this tends to be a challenging thing for students. So let's see another example of that beyond what we have done in class. Okay, so here's the proposition we are going to consider. For every even positive integer n greater than 2, there exist prime numbers p and q such that p plus q equals n. So hopefully you can see the two quantifiers involved in this statement. Really, there are three. N is universally quantified, and p and q are both existentially quantified. Okay, now this again, it's not some random statement that we just, pulled off the street. This is one of the most famous statements in mathematics. It is known as Goldbach's conjecture, proposed back in the 1700s in a letter that Goldbach wrote to Leonard Euler. Goldbach thought it should be true. Euler agreed. He thought it should be true as well. And Euler proved a lot of things, but he wasn't able to prove this, and neither was Goldbach. And in fact, in the 300. Around 300 years since then, no one has ever been able to prove Goldbach's conjecture. Now, you can certainly look at evidence here. So, for instance, we could say, well, let's try out some n's here. N has got to be an even positive integer greater than 2. So we could say, well, what about 4? That's the smallest element of that domain. And you could say, well, I can take p and q to be 2 and 2. No one said that the primes have to be different, so 2 plus 2 equals 4. And we got that case taken care of. You say, well, what about 6? Well, 6 is equal to 3 plus 3. And I need to try 8. 8 is equal to 3 plus 5, or vice versa. 10 is equal to 5 plus 5. Okay, and you can keep going like that, and people have. And so have computers, and they've taken this up into the billions. And it, so far, every even integer that you try that's greater than 2, it's been expressible as a sum of 2 primes. But as we know, this statement, it's a universally quantified statement. It doesn't matter how many examples you give, that is not enough to show that it's true. So even checking this all numbers up into the billions, it's not a proof. It does not guarantee that this is going to be true for every even positive integer greater than 2. So let's suppose that you wanted to become famous, and to obtain your fame, you are actually going to try to disprove Goldbach's conjecture. It would be a shocking, unexpected result that would catapult you instantly to fame if you could do it. Well, if you wanted to disprove Goldbach's conjecture, that means you would have to prove its negation. And that means you are going to need to negate it. So let's negate Goldbach's conjecture. Again, we'll take it one step at a time. You see the for every there. That's our universal quantifier. And so we know that that's going to flip and become there exists. Okay, and now we look at what comes next. We have our domain specification here. And our domain is the set of even positive integers n greater than 2. So all the rest up to the comma there, that is all the indication of the domain over which we are universally quantifying. Okay, so this is the domain. And if we wanted to, we could give a symbol to that. This would be 2 plus 2z plus. This will take our positive even integers and add 2 to all of them, so that now the smallest element is 4. Now, when you are negating, the domains should be the easiest part because they never change, okay? We flip all the quantifiers, but the domains are still the same domains. We still want this statement, this negation, to concern the same domains as the original. So we could say there exists an, we better put an in there to be grammatically correct, even positive integer greater than 2. And it'll go down here. Okay, now there's our domain. And next in the original, we see a comma. But now the comma was the bookend for the universal quantifier. When you negate, you switch the quantifiers. It's also important to switch the bookends. Otherwise, you end up with something that grammatically is very awkward and incorrect. So now that we've switched this to an existential quantifier, the bookend for that is a such that. And so the comma changes to a such that. Okay, next up we see there exist, prime numbers p and q. Okay, so there exists is going to change to for all. Okay, and we kind of condense things a little bit in the natural language here. Really, we are switching 2 quantifiers here. There are 2 there exist quantifiers. Both p and q are existentially quantified originally, so now they're both going to become universally quantified. The domain for p and q, for both of them, is the set of prime numbers. We can just continue to express that in natural language here and say for all prime numbers p and q still have those same 2 variables over the same domain. Okay, next we see such that. Now such that, this was the bookend for those existential quantifiers, which we have switched to universal quantifiers, and that means we need to switch the bookend as well. And the bookend for a universal quantifier is a comma. 1 comma suffices for both of them here in natural language. Okay, and then we have our property. Okay, the property here, the predicate, is p plus q equals n. Properties need to be negated as well. And the negation of p plus q equals n would be p plus q does not equal n. Okay, and there we go. So here's the negation of Goldbach's conjecture. There exists an even positive integer greater than 2. Oh, I forgot to put n in here. There exists an even positive integer n greater than 2. Got to have the variable in there for standard form for sure. Greater than 2 such that for all prime numbers p and q, p plus q is not equal to n. Okay, so to disprove Goldbach's conjecture, you can see here exactly what you would need to do. All you have to do is find one example of an even positive integer greater than 2 that for all prime numbers p and q do not add up to n. It may sound kind of easy, perhaps, but it's not, and no one's ever been able to do it, including with computer assistance. So even though it's an existentially quantified statement now, that does not make it at all easy to prove. And again, just about everyone believes that the original Goldbach's conjecture is true, and so this negation would be false. You could search for your whole life for an example to prove this statement, and you may never find one. But there's always that slim chance you could become famous if you do, and so it'd be kind of like playing the lottery, I suppose. Okay, hope you enjoyed this extra example video, and see you again soon.